In this video, I'm going to show you how to solve constant coefficient differential equations like this one. This is a constant a times y double prime, a constant b times y prime, and a constant c times y is equal to 0. So the approach that we took previously, and we'll do it again here, is to guess a solution of the form e to the rt. It's just a guess. We'll see whether it works. But if I do this, then I can substitute this in. Two derivatives of e to the rt is r squared times e to the rt. There's a constant a out the front. Then one derivative of e to the rt is r times e to the rt with a constant b out the front. And then cy just becomes c e to the rt, and all that adds up to 0. I cancel the e to the rt's, which you could do immediately, by the way, after the first few tries of this. The e to the rt's always cancel. And that leaves me with the so-called characteristic equation, and it's a polynomial. ar squared plus br plus c is equal to 0. This is just some polynomial in r. And then the good news is, for a quadratic polynomial like this, we can always solve it. We have the quadratic formula. We say that r is equal to, well, you know the drill, minus b plus or minus square root of b squared minus 4ac all over 2a. Maybe you can sing-song the cadence of that with me if you've said it enough times in your past. So it's the quadratic formula. So in general, if you knew the a, b, and c, now you would know the roots. You would know the specific r's to plug into your e to the rt. However, there's actually a bunch of different cases for how a quadratic formula like this is going to work out. And in fact, there's precisely 3. One option is about what we call the discriminant, the thing inside of the square root, the b squared minus 4ac. If that's a positive number, then what you have is actually 2 different real values, what we call real and distinct roots, because it's like minus b plus or minus some real number. So that's when the portion under the square root is positive. You get these 2 different real values. If the portion under the square root was 0, you'd be like minus b plus or minus 0. That wouldn't give you 2 solutions. That would only give you 1 solution that we call repeated. It'd be the same root, r minus whatever this root is, but it would be r minus that root squared. It would be repeated. Then the third possibility is, well, if the b squared minus 4ac is less than 0, if it was negative, then you'd have square root of a negative value. That is, this is a so-called complex pair, plus or minus I times something. So these are 3 possibilities, and what I want to talk about is, well, for each of these possibilities, what does the general solution to the original differential equation look like? Now, to motivate this a little bit, I want to go back and remind you of the theory that I talked about a couple of videos ago. And it said, if I'm talking about a generic second-order linear differential equation like this one, this, by the way, isn't even constant coefficients. You're allowed a generic p of x and q of x if they're sufficiently nice. But constant coefficients are an example of this. And then it says, if you have 2 solutions, y1 and y2, they're linearly independent, which means they're not just like a multiple of each other. It's not like one is just like twice the other. So 2 different linear independent solutions. Then your final answer, your general solution, is just a linear combination of those 2 that you found. c1 times y1 and c2 times y2. General solutions means any solution can be written in this way. So what we're looking at for our second order constant coefficient differential equations is we're trying to find those 2 linearly independent solutions. Find those, and that's what you need for your general solution. So how do I find them? So the 3 cases. First case was the b squared minus 4ac greater than 0, and you got those 2 distinct roots. So like an r1 and an r2. Then the general solution is exactly like what we saw in our first example of this concept, the previous video. It's just e to the r1t with the constant, and then a different constant e to the r2t. If they're real and distinct, it's easy, nothing to do. So next case is you have a repeated root. That's when the b squared minus 4ac was equal to 0. You're taking plus or minus 0. So there's not 2 different things, there's only 1. So what can you do? I mean, one solution would be e to whatever that root r times t would be. But what about the other? So notice this trick that we do here. The trick is, I'm going to take the e to that root rt. Notice there's no longer an r1 and an r2 here because there's only 1 root. It's a repeated root. So the first one is exactly the same, c1 e to the r times t. But for the second one, I do a little trick. I can't do e to the rt again. I can't do that again because that would not be a second linearly independent solution. So I try t times e to the rt. And t e to the rt gives me that second solution. You might be thinking, hold on here, you need to do a little bit more arguing. Why is this true? Well, it's true for two reasons. First of all, t times e to the rt is a solution. Don't believe me? I would encourage you to just check it out. Take the two derivatives, take the one derivative, plug it in. You're going to have a bunch of product rules, so I'll leave it as an exercise, but it's all going to cancel out exactly the same. If e to the rt is a solution, t e to the rt is as well. And then secondly, e to the rt and t e to the rt, those are not linearly dependent. That is, one is not just a constant multiple of the other. I understand one is t times the other, which might make it seem like it's linearly dependent, but the definition of linear dependent was that the one function is not a constant times the other. This case is one function being the variable t times the other. It is linearly independent. So I have two solutions, they're linearly independent, and thus my general solution is a linear combination of those two solutions. That's how you solve the repeated root situation. All right, case 3, this is the fun one. We're going to talk now about the complex pair when b squared minus 4ac is negative and you have square root of a negative value. Well, in general, a complex number, I will write it this way. The root is alpha, that's the real part, plus or minus I times beta, that's the imaginary part. So my alpha here and my beta are both real numbers, and the form of the quadratic formula gives you that real part. That's the minus b divided by 2a, that's the real part. And then it also has this complex part, which is the square root of the b squared minus 4ac divided by 2a. That'll be like I times a number, and it's a plus or minus. Okay, well, if we were just doing what we did before, we'd just plug this in. We'd be like c1e to the first root times t, c2e to the second root times t. And actually, that's a fine answer. But we're going to do a little bit better, because when we're trying to model physical behaviors, we often want to have our output be real valued. So how do we do this? We want to ensure that our constants C1 and C2 are real valued. We want to ensure that our exponentials are real valued, because we're going to be modeling real things, like the quantity of a population, for example. So let's just zoom in on one of these first. I'll do the e to the alpha plus I beta multiplied by t. Now, the first thing I'll do is just a little trick of exponents. I have a sum in the exponent, and that's the same thing as just multiplying the base. E to the alpha times t multiplied by e to the I beta times t. The e to the alpha t is just going to be a constant at the front. Let's just ignore that. That's all real. What about e to the I beta t? Well, e to the I something, e to the I theta, say, that should have a bit of an alarm bell, because we have Euler's formula. Euler's formula tells us how to deal with e to the I times something, and it works like this. It's cosine of that something, in this case beta t, plus I times sine of the beta t. And then out the front, I've got the e to the alpha t. As I said, that's just going to stick out the front. So we have used Euler's formula to turn the exponential with an imaginary argument into a cosine term and I times a sine term. That's my y1. I can do the exact same thing with the minus signs. It works basically the exact same way. The only difference is that because cosine is an even function, cosine of minus beta t is the same thing as cosine of beta t. But sine is an odd function, so sine of minus beta t is negative sine of beta t. So that's why the negatives work out the way they do. Okay, so I got my y1 and my y2, but they are still both complex. I mean, there's i's involved in both of them. So here's the real trick. So let me simplify just a little bit. Let me consider y1 plus y2 divided by 2. Well, the first thing I'm going to note is this is a solution. Has to be a solution because if you have a solution, any linear combination of solutions is a solution as well. That's part of our theory. So this linear combination of solutions is a solution. Well, let's see what it does. Well, the plus and the minus and the signs, they cancel. And all I'm left with is 2 e to the alpha t cosine of beta t and divided out by 2. The 2's cancel. Okay, that's great because that is entirely real. Let's do another trick, kind of in the same way. This is a little bit of a tricky method. y1 minus y2 divided out by 2i. Again, a linear combination of solutions. It has to be a solution. Well, in this case, now the cosines are going to cancel. The sines are getting multiplied by 2. But you divide out by the 2i and you get rid of the I and you get rid of the 2. And what do you get? E to the alpha t times sine of beta t. Another real solution. So what I have here is two different solutions. They're both real valued, so there's no imaginary numbers in sight any longer, right? Alpha and beta were both real. So they're both real. They're both linearly independent. I mean, clearly the one is not a multiple of the other. Cosine is not twice sine or any other multiple of sine. And they're both solutions because they're linear combinations of solutions. So this satisfies our theory. We have two different linear independent solutions to our ODE. So why don't we just choose those two instead? Okay, so going back to my previous slide where I'd shown the previous way I guessed it with the e to the alpha plus I beta times t and the e to the alpha minus I beta times t, I'm going to replace that. I'm going to replace that with those new solutions we found. We have one constant c1 times the first solution, which was an exponential and a cosine, and then a c2 times the second solution, the exponential and the sine term. That is my general solution in the case where I have a complex pair of roots. All right, so let's think a little bit broadly for a moment. We've said that for a second order constant coefficient differential equations, you get the characteristic equation. Those are three cases: two different distinct real roots, one repeated root, and a complex pair of roots. And what we've seen for each of those three cases is how we can break it down and get the standard general solution in each of those three cases. In the next video, we're going to see a couple concrete examples of this, and we're actually going to jump from second to third and fourth and beyond order constant coefficient differential equations as well.